I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
The most familiar instance of conservation of energy is probably when stuff is falling from the sky and it picks up speed on the way. So let's explore that example a little bit more. So here we have a box at, let's call this altitude or height y2, and then the rest position is called that y1. So we have some zero level at some arbitrary height like this. And this box acts a little bit weird. As you can see, it doesn't fall straight down, but it goes on this arbitrary path. But let's denote this displacement from the initial to the final position as one vector. So we just call it delta x in x direction plus some delta y in the j direction. So this is our coordinate system, x and y. And at every point on this path, there is a force acting on the box, which is gravity, and it's always downwards in this case. So we call it just minus mg j. Magnitude is mg, and minus because it points down, our positive direction is up, and j gives the sense that it's always vertical. So how much work is now done on the box when it falls down? So the amount of work is whatever the force is, and dotted by this displacement vector like this. So let's put them in. So this was F. So minus mg j dotted by this displacement vector and as you know, the dot product is non-zero only for the similar components. So when we're dotting with j with this I, that gives us only 0. So only term that we have left is the combination of the j terms. So just mg from here multiplied by the magnitude of the other j vector, delta y. And what is delta y? So that's the change in the height. So final minus initial. Okay, of course, this is a little bit misleading now. So let's fix that one. So of course this is the final altitude, and then the initial altitude or height is like this. And we get mg y1 minus mg y2. So this is the work done on the object by gravity. And what is interesting about this result, not only do you recognize it as a difference between the potential energies at the 2 points, but also that the displacement in the horizontal direction didn't affect at all. So in other words, it didn't matter what path it took to get to the final altitude or final height from the initial height. only the difference between those two heights. And this is one property of a conservative force. And here is the formal checklist for the work done by a conservative force such as gravity. So let's go through this list. First, the work can be expressed as the difference between the initial and final values of a potential energy function, just like we have here. So that's a check. It is reversible, so this means that it can be recovered. So for example, imagine this was a ball instead of a box. A ball would bounce from the ground, and with the speed that it has, it bounces back up. So in that process, the initial potential energy is converted into kinetic, but the kinetic is converted back to potential by the force itself, and it recovers everything that was in the beginning. In essence, it bounces back to the same height. So gravity fulfills that condition. Also, the work is independent of the path of the body and depends only on the starting and ending points, just like we saw here. It doesn't depend on the horizontal displacement, only on the vertical, and indeed only the initial and the final points. Okay, and then when the starting and ending points are the same, the total work is 0. So when y2 equals I1, that's going to be 0. Okay, so in gravity we have a conservative force. Another example is, let's say, the elastic work done by a spring. You remember that we had this result, the work done by a spring. So when we have a wall and some spring, and let's say we have an initial x equals 0 there, so that displacement is x1, and then it is pulled back to some final position x2. In that case, it's almost same as the ball was, or the box was falling from the sky. The spring is pulling the mass back, but it can also rebound it to exactly the same initial position if no other losses are considered. All the experiments done to this day on objects that are only under the influence of conservative forces, the following has been observed. So the change in the object's kinetic energy plus its change in potential energy, for example, as given by one of these functions, is constant. Basically saying that the energy is being conserved. But of course there are forces that are not conservative. For example, forces that cannot be described by potential functions, or they are not reversible. The best example is, of course, a friction force. So let's say we have a box sliding on the floor, and it has some initial velocity. It slows down due to the friction, and some of that, or the energy that is being lost, it's not lost, it's pretty much converted into heat in the box and the surface. But it never happens that all that heat is somehow summoned back to accelerate the body to its initial velocity. Another example of non-conservative force is if you have an explosive. There's a lot of chemical energy stored in the explosive, and then it goes off. It suddenly increases the mechanical energy of those fragments, but the fragments are never going to assemble back into a firecracker. It is clear, however, that the work done by non-conservative forces affects the energy balance of our system, and it has to be taken into account. And we do it in the following way. So instead of only have kinetic energy of the objects and their potential energy, we also have to consider the internal energy of the objects involved. So internal energy in the examples that I just explained to you would be temperature in the case of friction, or the chemical energy stored in the explosive. And those can be converted into a kinetic or potential energy. So, okay, let's fix this. So the sum of the changes is not only constant, it's of course zero. So this is the law of conservation of energy in the universe as we know it. Oftentimes when we solve mechanical problems or mechanics problems, however, we don't explicitly talk about the temperature or the chemical energy stored in these bodies, but we just consider the work done by them, or the work lost to the temperature, for example. And in this case, we use this alternative formulation: the sum of kinetic energy plus potential energy plus work done by other forces than conservative ones equals zero. And if you write this out using these gravitational and potential energy terms, we can do it in the following way. So first of all, kinetic energy at the beginning plus some elastic energy, if that's included in the system, all at initial point v1, x1, h1, plus any other work that is done, could be friction, for example, equals kinetic energy plus some elastic potential energy. That's of course at point 2, and potential energy at the point 2. This formulation can of course be supplemented with some other forms of energy related to other conservative forces, for example electrical potential energy. But that is a topic for another course, and this formulation is the cure for most of our problems in mechanics. We try.